Here we are going to check whether the vector in item B, which is 6, 11, 6, is a linear combination of the vectors u, v, and w. To show, we need to make sure that we could locate or identify k sub 1, k sub 2, and k sub 3 to exist that will satisfy the next equation I'm going to place. Now, there are three of them because there are three vectors, and we're trying to identify whether these three vectors could result to 6, 11, and 6 together with the scalar. So again, we need to look for k sub 1, k sub 2, and k sub 3, which will satisfy this equation here. 6, 11, 6 is equal to k sub 1u plus k sub 2v plus k sub 3w. Okay, so we need to show or we need to see if they really exist, and if they exist, and what are the values, and then later on decide whether 6, 11, 6 is a linear combination or not. So we can apply here or substitute the values for our vectors 2, 1, and 4, plus your k sub 2 times 1, negative 1, and 3, plus k sub 3, your w is 3, 2, and 5. Since we already assumed that k sub 1, k sub 2, and k sub 3 are scalars, so we can apply here scalar multiplication. So this is still 6, 11, 6, which will equal to 2k sub 1, k sub 1, 4k sub 1, plus k sub 2, negative k sub 2, 3k sub 2, plus 3k sub 3, 2k sub 3, and 5k sub 3. Then we use the vector addition here. 6, 11, 6 still is we have 2k sub 1, all the first entries, plus k sub 2, plus 3k sub 3, comma. Next entries, k sub 1 minus k sub 2 plus 2k sub 3. And then the last entries, 4k sub 1 plus 3k sub 2 plus 5k sub 3. And then since we assume that they are equal, so we can say that this here is equal to 6, and so on and so forth. And just by arranging it, symmetric property, I have here 2k sub 1 plus k sub 2 plus 3k sub 3 is equal to 6. Next, k sub 1 minus k sub 2 plus 2k sub 3 is 11. And then 4k sub 1 plus 3k sub 2 plus 5k sub 3 is equal to another 6. This is now a system of linear equation where we have here our variables k sub 1, k sub 2, k sub 3 that we are trying to solve. So we need to use here this augmented matrix equivalent for that. We have 2, 1, 3, 6, the coefficients, 1, negative 1, 2, 11, and for the third row, 4, 3, 5, and 6. Okay. Then we are just going to use the Gauss-Jordan elimination to come up with a reduced row echelon form of this, so that we could really see if k sub 1, k sub 2, and k sub 3, all of them should exist. So to do that, let me first interchange row 1 and row 2 so that I will have leading 1 for my first row. So it will be 1, negative 1, 2, 11. Then 2, 1, 3, 6, 4, 3, 5, and 6. And then applying the appropriate elementary row operations to make this zeros. So I'm going to multiply negative 2 to row 1, add it to row 2 for a new row 2, and we also multiply negative 4 to row 1, add it to row 3 for a new row 3. So row 1 is the same, 1, negative 1, 2, 11. So negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times negative 1 is positive 2 plus 1, 3. Negative 2 times 2 is negative 4 plus 3, negative 1. And then negative 2 times 11 is negative 22, plus 6 is negative 16, right? 11 times negative 2 is negative 22 plus 6, so negative 16, that's correct. For our third row, negative 4 times 1 is negative 4 plus 4, 0. Now, we have zeros after or below our leading one. Continuing, negative 4 times negative 1 is 4 plus 3, 7. Negative 4 times 2 is negative 8 plus 5. Negative 8 plus 5 is negative 3. Negative 8 plus 5, yeah. Next, negative 4 times 11 is negative 44. Negative 44 plus 6. So you have negative 30. Okay. Next here is to multiply 1/3 to row 2 for new row 2 so that this would be another leading one. I'm not going to apply any other operations yet. So we have negative 1, 2, 11, then 0, this will become 1, negative 1/3, negative 16 thirds, 0, 7, negative 3, and negative 38. Next is to multiply negative 7 to our row 2, add it to row 3 for a new row 3, okay, to make this 0. But be careful because you have a very large fractions here later. But anyway, let's do it like this. 1, negative 1, 2, 11. Next, second row is a 0, 1, negative 1/3, negative 16 over 3. 0 still here. So negative 7 times 1 is negative 7 plus 7, 0 now. Next, negative 7 times negative 1 is positive 7. Negative 3 in terms of denominator 3 is negative 9. So we have positive 7, negative 9. So we have negative 2/3. Okay, let's check here. Here comes the thing that I am talking about. So I don't have a calculator here, so let's do it like this. Negative 7 times negative 16. So you have 16 times 7. That's 2, 4. So you have, sorry. Okay. I have 111. So positive 111 over 3. Okay. But 38 here. So negative 38 or 38 multiplied to 3. That's 4, 2, 114. So notice you have 114 over 3. But specifically negative 114 over 3 and positive 112 over 3. That's again negative 7 times negative 16 is positive 112 over 3 here. And then add it to negative 38, which is negative 114 over 3. So you have negative 2/3. So of course, operations of fractions is very important. Now that we are done with this, I will multiply negative 3/2 to my row 3 for a new row 3. So you have 1, negative 1, 2, 11. 0, 1, negative 1/3, negative 16 thirds, 0, 0. This is 1, this is 1 as well. So we are done with our K sub 3, our third, what do you call this one, scalar, the one of the three that we're solving for. But let's just continue forward, even if you could substitute here on the next two equations or equivalent equations later. Let's just simply move forward, and I'm going to multiply 1/3 to row 3, add it to row 2 for a new row 2, and to make this 0, or by the way, there's 1 there, and as well as multiply negative to row 3 plus row 1 for a new row 1 to make this 0 as well. So I have here this version. Since it's the third row that I'm not manipulating, I'm going to write it immediately. This is 0. 1/3 times 0 plus 1 is still 1. Here comes the thing. 1/3 times 1 is 1/3 plus negative 1/3, 0. 1/3 times 1 is positive 1/3 plus negative 16 thirds. So that's negative 15 thirds or negative 5. So this is still 1 here. because negative 2 times this here is still 0. So negative 2 here, so it is still negative 1. Negative 2 times 1 is negative 2 plus 2, 0. Negative 2 times 1 is negative 2 plus 11, 9. I have 9. And then to remove this finally, I'm going to simply add row 2 and row 1 for a new row 1, and let me place it here for I don't have space anymore. So we have 0, 0, 1, 1 for our third row. Our second row is still 0, 1, 0, negative 5. 0 plus 1 is 1. Negative 1, 1 plus negative 1 is 0. 0 plus 0, 0. Negative 5 plus 9 is positive 4. This is already a reduced row echelon form. And with this, going back to our original system, k sub 1, k sub 2, and k sub 3 here, that also corresponds to these coefficients. In short, k sub 1 is 4. K sub 2 is negative 5. It's negative. And k sub 3 is positive 1. All three of them exist. This satisfies the idea that, going back here, our vector of 6, 11, 6 is yes, it is a linear combination of vectors u, v, and w, since we already solved for this scalar that will represent this equation. Thank you very much for watching.